Hey everybody, welcome back to chemistry. And now what I want to do is talk about a particular problem that you're looking at on your Achieve homework that has to do with finding the velocity of a molecule. So let me just kind of tell you what the problem is right here. It says as follows. What is the root mean squared velocity of a nitrogen molecule at 25 degrees Celsius? Okay, so let me go to the board and solve that. All right, so there is a particular formula you need to apply to solve this problem. So let me give that formula to you. And it is V for velocity, RMS stands for root mean squared, is equal to the square root. And we have 3 times R, which is the gas constant, times T over a weird looking M, looks like that. And that will be the molar mass. Okay, so now what I need to sort of point out is some of these variables here, they're not what you normally would expect. So for example, in past problems dealing with gas laws, when you used R, the value was 0.08206 liters atmospheres over moles of degrees Kelvin. But here, that is not the constant we're using here. We're going to use a value of R, but it's different than the one we're used to. So let me give you that. Is 8.314 joules over moles times Kelvin. So T here will be in Kelvin. And then M is going to be the molar mass. But here's the thing, the molar mass will not be in the typical units, which are grams per mole. Instead, we have to use special units, which are kilograms per mole. So just a note here, the units here for molar mass must be kilograms per mole. Okay, so now what I want to do is just take a moment and sort of explain why is it that we sort of have these unusual units we're using with this problem. So let's just go ahead and just put in the units and see how they cancel out and see if they give us what we hope for, which is a velocity. Okay, so here we go. So we have a square root, and we're going to have a 3 here. We're only going to be talking about units, so I'm going to leave out the 3. And so what is R here? R is joules over moles times Kelvin. And then T is Kelvin, that will be in the numerator. And then here in the denominator within the square root, we have kilograms per mole. And what we hope is that these units in the radical here will cancel out such that you're leaving units that are good for velocity. And the units we're kind of hoping for velocity would be meters per second. Okay. So let's just go ahead and try to cancel out some units and see how far we get with that. Okay, so let's see. So it looks like Kelvin cancels out, right? And then mole cancels out. But right now, I cannot cancel out joules and I cannot cancel out kilograms. So right now, what I have, or I'll write this over here, is meters per second, which would be the velocity. That's what we want. Is going to be equal to the square root of joules over kilogram. Okay, so one question we might want to ask is it possible that joules per kilogram and a square root can be converted to meters per second? And that is the case. So let me explain how this is done. So we have to go back and remind ourselves of something we learned about in chapter 6, which is work is equal to force times distance. Okay, and so what force is equal to mass times acceleration, which is the second law of Newton. This is something that you're going to learn about in physics class. We probably didn't really talk too much about in this class. So times distance here. Okay, so let's go ahead and look at the units here. And so mass is going to be in kilograms. A for acceleration is units for that, and the SI units for that are going to be meters per second squared. You'll learn about that in physics, meters per second squared. And then distance will be meters. Okay, so let's go ahead and combine these, and what you get here is kilograms meters squared over seconds squared, all right? Now, one of the things I think we learned in chapter 6 is that when you have these units, kilograms times meters squared over seconds squared, that is defined as a joule. So this is a joule. And which makes sense because work is going to be equal to mass times acceleration times distance. And so we know work is in joules, and the reason is because joules has been set to be kilograms meters squared per second squared. Okay, now the final step is let's see what happens when we move here kilogram to the other side of the equal sign. And so what we get is joules divided by kilograms is equal to meters squared over seconds squared. Okay. So I think you can sort of see now that what we can do is we can substitute in meters squared over seconds squared for joules per kilogram. And so when you do that, so again, joules per kilogram is equal to meters squared per second squared. And so now I think you can see that when you take the square root of meters squared per second squared, you get meters per second. So just to make a long story short, when you use R in joules per moles degrees Kelvin, and when you use molar mass in kilograms per mole, the units will cancel out in such a way that in the end, after you take the square root of the number in here, you will get units of meters per second. Okay, so let's go ahead and solve the problem. Let's go ahead and put up the equation again. It's 3 times the gas constants R times T over the molar mass. Okay, so let's go ahead and put in some numbers here. Okay, so it's the square root of 3. R is 8.314 joules per moles times Kelvin. And T, okay, so now we need to get temperature into Kelvin. So that's going to be what? 25 degrees Celsius plus 273.15. And so I'm going to add those up, and then I'm going to round this to correct number of significant figures. I'm doing it this time because that's the way the book does it. And so when you do that, I get 298 degrees Kelvin. Okay, so this is going to be 298 degrees Kelvin. And I'm going to divide that by the molar mass. And so you have to remember here that we must convert molar mass into kilograms per mole. So let me go ahead and do that now. So one of the things I note here is that we know the identity of the molecule. It is a nitrogen molecule, so nitrogen molecule is N2. Okay, so you can figure out the molar mass for this in grams per mole. And so what you would do is just take the average atomic mass of nitrogen, which is around 14.01, and you multiply by 2. And so I think that would work out to be 28.01 grams per mole. I think that's what is pretty close to. Okay. And then you need to get this into kilograms per mole. So let me go ahead and do that. So you would take this number here and multiply it by 1 kilogram over 1,000 grams. And when you do that, what you should get is the molar mass of nitrogen in kilograms per mole is 0.02801 kilogram per mole. Okay. Now, what I'm going to do now is substitute in this molar mass in kilograms per mole right here, which is 0.08201 kilograms per mole. So what I'm going to do next is I'm going to do the math. And so I worked this out earlier. What I got in the square root, I got 2.655 times 10 to the 5. And again, I think what you can sort of see here is that looks like moles are going to cancel, and then Kelvin's going to cancel. And so units we have here are joules per kilogram, right? But we've kind of figured out earlier that those units, 2.655 times 10 to the 5, these units here, joules per kilogram, that is just meters squared per second squared. Anyway, so when you take the square root of that number in there, in the end, what you should get is you're going to get about 515, and then you're taking the square root of meters squared per second squared, and so you could be about 550 meters per second is the answer. So interestingly, in miles per hour, that's about almost 1,200 miles per hour. So right now, you are being struck by nitrogen molecules. They're at room temperature, and they're going on average as fast as 1,200 miles per hour. So you might wonder why that doesn't hurt you. And the reason is because the molecules have such a itty bitty mass that even though they strike you with that high speed, you barely feel a thing. Okay, thank you for listening. We'll talk to you next time.